Hi everybody, this is section 5.2 and we are going to look at properties of functions in our Hawkes Learning College Algebra textbook for Math 101. So the first thing we're going to look at is symmetry for functions, and the first one we're going to look at is y-axis symmetry. And a graph is symmetrical with respect to the y-axis if the opposite of x, the function, so if you were to plug in the opposite of x, it's the same as x. Now that means, like, if I were to plug in, if you look here, we have a parabola that is symmetric about the y-axis. So if we look here, here's our y-axis, and here is our parabola. All right, now if I were to look at, and what they're saying is if the function of the opposite of x is equal to the function of x. So if I were to plug in, and I'm going to erase it a little bit so we can see a little bit better. Let's see here. If I were to plug in, I'm looking for one where it's a nice number. Okay, so if we look right here, if x was 2, we can see, just by looking over, that y would be 4. Now, if x is the opposite of 2, or negative 2, y is still 4. And you can look here, again, we're going to say this is approximately like negative 1.5, and then 1.5, they both equal 2. So that's what they mean when they are saying that it is symmetric with respect to the y-axis. So if I were to fold, if this was a piece of paper and I were to fold the paper on the y-axis, both sides of the graph would match up to each other. They're almost, it's like they're mirror images of each other. And any function that is symmetric with respect to the y-axis is an even function. So it would be considered an even function. All right, next we are going to talk about origin symmetry. So a graph can have origin symmetry, so it's symmetric about the origin. And if it is symmetric with respect to the origin, which, remember, your origin is that 0, 0, right where the two lines cross, then the opposite of x, the function, the opposite of x, is going to be equal to, and here it's going to be equal to that opposite of f of x, or kind of think of it like the opposite of y. So like that opposite of y right there. And this is an odd function. And really what I want you to look at when you look at this graph is you can see they're no longer, if I were to fold this on the y-axis, I would not have the same thing on both sides. But now my graph goes from, it spans the length of the y-axis, and it goes from the top of the y-axis through that origin and then down through the other side. So it's symmetric about that origin. All right, so on the last two slides, we looked at symmetry for functions. And remember, in order for something to be a function, they have to pass that vertical line test. Now we're just going to look at symmetry of equations. Not every equation is a function that doesn't pass the vertical line test. But we have equation symmetry if, for that y-axis, if replacing x with the opposite of x results in an equivalent equation. So again, we talked about, like, if x was 2 and then x was negative 2, you would get the same result when you plugged it into your equation. Now, equations are symmetric about the x-axis if you replace y with the opposite of y. So if I solve an equation and get 5, and then I solve another equation and get negative 5, again, it would be that same equation. And then our last one is an equation is symmetric about the origin, which we know is our odd functions, if we replace x with the opposite of x and y with the opposite of y. And it results in an equivalent equation. And we're going to take a look at some of these examples to see, because I know kind of just listening to it is a little hard, but we're going to take a look at a couple examples. All right, now we will be looking at these three equations to see what kind of symmetry they have. We have two functions, a and b are both functions, and c is just an equation. And we're going to look at them using the graphing calculator, and I will show you videos of how to graph them. But if you don't have a graphing calculator and you want to sketch them, really to start, you can plot points to help you understand or look at the basic sketch. Plotting those points will kind of help you out, figure out an x value, then find y value. You don't, I would say like plot 4 or 5 points to kind of help you sketch the graph. But we are going to, instead of sketching them, we've done sketching of graphs. We don't need to. We are going to look at the graphing calculator to do this. All right, so here we have the first function, f of x equals 1 over x squared. And I went ahead and posted the graph of it. But again, I would encourage you to use your graphing calculator or an online graphing tool to help you view this instead of plotting it by hand for now, because really we want to focus on that symmetry. In the next slide, I have posted a video on how to graph it on the graphing calculator, so you can take a look at that. But here, when we look at this, this equation is an even powered equation, a function, and it is symmetric about that y-axis. So we can look at this, and if I were to take it and fold it on the y-axis, both sides would match up and be exactly the same. So this one, it's an even function and it's symmetric about that y-axis. All right, so here is the graph for x cubed minus x. And again, I would encourage you to use a graphing calculator. I did post on the next page how to graph it using the graphing calculator. But if we take a look at this equation, it is an odd numbered equation because both powers are odd numbered. We have a 3 and a 1. And so it is symmetric about this origin right here. And again, if I were looking at this, we have part of the graph that extends all the way through that y-axis. It goes up the y-axis, but then also if we look the other side through that origin, again, it's like a mirror image but flipped. It is, so this one is symmetric about the origin. All right, so for this one, we have x equals y squared. Now, if you notice, when we did the graphing calculator before, it was y equals. So really what we would have to do is, what this is it's not a function because it doesn't pass the vertical line test. It is, it's like the inverse to the x squared function, but it's not exactly an inverse because, again, it does not pass that vertical line test. Excuse me. So it's not a function to begin with. However, when we look at this one, this is one where it's an equation and it is going to be symmetric about that x-axis. Because again, if I were to fold my paper on this x-axis, then it would be symmetric about the x-axis. So that both sides would be mirror images, or they would look like one single graph when I fold it on that x-axis. So really here is an example of something that is symmetric about the x-axis. And again, to do this, you could plot some points to find it. You could solve the equation for y, but that's going to get a little messy. Or, sometimes looking online at graphing tools will help you graph this as well. But again, for like hawks, I would graph some points to kind of sketch what it looks like. All right, next we are going to look at something called intervals of monotonicity. I have a hard time saying it, but what it is we're looking for where a function is increasing, decreasing, or constant. So, if it's, I always think of it this way, if it's an increasing, it's going, you read a graph, remember, from left to right, like you read pages in a book. So if it's increasing, it's going up from left to right. If it's decreasing, it's going down from left to right. And if it's constant, it would stay steady. It would be like your horizontal line. We are going to take a look at all of those in the next few slides. All right, so now we're going to look for the open intervals of monotonicity for the function f of x equals x minus 2 squared minus 1. Now, we can see it's been graphed, and we can see that we have a parabola here. So they've graphed our parabola. We do know from our equation, because it is in vertex form, that the vertex of the equation is 2, negative 1. Our vertex is right there. Now, again, you read a graph from left to right. So if I look at this parabola right here, down to the vertex, that's kind of like where it bottoms out because it opens up. So on this part where it's red, this line, as I go from left to right, is decreasing. So this would be where the interval is decreasing. And it is decreasing from negative infinity, because we have that arrow there. So it would be negative infinity to 2, because you're always going to use that h value to help write our intervals. And again, it wouldn't, it doesn't include 2 because it stops there, so we put the parentheses there. But then from 2, 1, our vertex, going from that bottom point, if we continue on from left to right, it is increasing from 2 to positive infinity. So we can see, again, you read it from left to right, it first starts going down where it is decreasing, but then from the vertex, it is going up or increasing. All right, so we are going to look at a word problem now, where we're going to look at increasing, decreasing, or constant. And here we have the water level of a certain river varied over the course of a year as follows. In January, the level was 13 feet. From that level, the water increased linearly to a level of 18 feet in May. So if I were to kind of just sketch this, and again, I'm only going to need like quadrant 1, so we're going to start here. But let's say here's January, and go with blue. Here's January, and the water level from January increased linearly to a level of 18 feet in May. Linear means like a line. So here's January, and here it goes all the way up to May. Pardon that little part. The water remained constant at that level until July. So constant would mean, again, that horizontal line. So May to July, it was constant, at which point it began to decrease linearly to a final level of 11 feet. So then until all the way to December. All right, so that would be our graph right there. Determine the water level as a function of time, or graph the water level as a function of time, and determine the open intervals of monotonicity. Well, here we kind of just sketched it, but what we would need to do is add in, down here we would put the months, and then we would need to do our water levels. So this we know would be 13, this one would be 18 up here. We'd want an even interval, in this down here would be our 11. And again, I just sketched it, so it's not perfect, but we will look at a graph in a minute to help us out with that. All right, so now what we need to do is we need to determine our open intervals of monotonicity. And when I sketched the graph, I said down below we'd have our months. Now, instead of representing them by the names, we often categorize our months by numbers, and this would help us better write our intervals. So if we're going to use 1 to 12 to represent January through December, our levels of monotonicity, we knew from January, so from January through May, they told us the water level was increasing. So that's our levels here, our interval would be 1 to 5. Then from May through July, which is the 7th month, it was constant. So it was constant 5 through 7. And then decreasing from July through December. So then our final interval would be 7 through 12. And that would show us our intervals of monotonicity through increasing, decreasing, and constant. And you don't always have, every graph doesn't have just increasing, decreasing, and constant. It may only be increasing, it may only be decreasing, or it may have a combination of both or all three. All right, and here is an official picture of the graph. And again, what they did is they put the months down here at the bottom, and they used numbers, so 2, 4, 6, 8, 10, and 12. They only numbered every other one. And then the water level. But again, you can see from January, the first month, that they started at 13 feet, and it increased to 18 feet in May. May through July, it was constant, and then July through December, it fell to 11 feet. Right, the next thing that we're going to look at is local extremes or extrema. And this is really, like if you look at a graph and it has, I call them peaks and valleys, that would be like where we find a localized either minimum or a local maximum value. They're called local extrema. And a graph could have several local extreme points. It could have a couple lows and a couple highs. We've already really kind of looked at this with parabolas, because with a parabola, we have a minimum or a maximum value, but other graphs could have more than just one minimum or maximum value. And we're going to take a look at a couple in the next graph. All right, so now we have a graph here, and they want us to find the locations and the type of local extremes. So here, and then determine the values of them. So if we look here at our graph, the first one, you're going to determine where they are. Really, the x value is going to determine the location. So if I'm looking to determine the location, look for that x value of them. And you can kind of see we here have a graph with 3 peaks or valleys. This first one here would be a local minimum, and its location would be -1. Then we have a local maximum, because it's kind of like, think of it as the top of a valley or a peak, and its location would be 2. And then we have another minimum here, because again, it's at the bottom of a valley, so its location would be 4. Now, so this is a max right here, this is a min, and this is a minimum as well. Now, to determine the values, really you're just going to look at what is the y value. So if the minimum is located at -1, the value of that local extrema is going to be the y value. So for this one, the first one, if the minimum is -1, the value of that extreme is -2, because that's where it hits that y-axis. Now for our maximum, the value is also going to be 2, because that is the y value for that. Think of it like that ordered pair. All right, and then for our other minimum, the local minimum of 4, the value or the y figure is 1. So 1 would be your value. All right, so the next thing that we're going to talk about, and the last thing in this section, is going to be the average rate of change. Now, sometimes when you're looking at a graph, you need to look at you just need to look at a portion of that graph. So you're going to look at the average rate of change. And the average rate of change of a function over a given interval, it really provides a summary of the function's behavior over that interval. So again, a graph may look different in different intervals, and we want to know a certain section, and we want to know what it looks like there. It's kind of like finding, average rate of change is kind of like finding the slope of that section, but not all of our sections are straight lines. So what we are doing is we are creating what they call a secant line drawn between the 2 points. So it's a line, a secant that is attached to those 2 points and drawn next to that interval. We are going to take a look next at a graph with a secant line in the next slide. But your average rate of change, you'll be given an interval, and it'll be interval A or B. Right now it's defined as A and B, where A cannot equal B. And to find that average rate of change, you're going to evaluate your function at B, you're going to evaluate your function at A, subtract those two values, and then divide it by B minus A. And we will take a look at this using numbers to help you see what it actually means. The letters get a little crazy at times. Okay, and so here you can see it's just a graph showing, we're finding the average rate of change and what it is between 2 points. So here is our secant line. It's a line drawn between those 2 points. Okay, and then we're looking at the average rate of change for this section of, it looks like it might be part of a parabola, but it's this curved part. So the average rate of change, again, it's not going to be exact for that curve, but it will be exact for that line. And that will help us gather some information about what we're looking at in the graph. All right, so the first thing we are going to do is we are going to find the average rate of change for the interval of 1, 3. So that means what we are going to do is 1 is going to be our first value, that's A, and 3 is B. So we need to first evaluate our function at 1 and at 3. So we are going to do f of 1 would be 3 times 1 squared minus 5 times 1 plus 2. And then we need to do 3 times 3 squared minus 5 times 3 plus 2. And when we do this, let's see here, we would end up with 3 times 1 squared. 1 squared is 1, so that's 3. And 5 times 1 is 5. So 3 minus 5 plus 2. 3 minus 5 is negative 2 plus positive 2 would give me a 0. And then next we have 3 times 3 squared. 3 squared is 9. 9 times 3 is 27. Minus 5 times 3 is 15. Plus 2. When I do 27 minus 15 plus 2, that is going to give me a total of 14. So remember, for the average rate of change, it is f of B minus f of A over B minus A. So we are going to have here f of B was 14. So we'll be doing f of 3 minus f of 1 over, and the A and the B, this is coming from this ordered pair. We're getting that value there, so it would be 3 minus 1. So f of 3 we know is 14, so we have 14 minus 0 over 3 minus 1. So that would give me 14 divided by 2, And my average rate of change here would be 7. All right, and now we're going to look at the average rate of change over the interval of -2, 2. And again, that -2, that's going to be our A value. B will be 2. And again, we want to do the function of B minus the function of A divided by B minus A. So when we evaluate, f of B is f of 2. So I need to do f of 2. I'm just going to plug it in. So we're going to do 3 times 2 squared minus 5 times 2 plus 2. And that will give me 3 times 2 squared. 2 squared is 4. 3 times 4 is 12. So we have 12 minus 10 plus 2. And that is going to give me 12 minus 10 is 2. 2 plus 2 would be 4. Then we need f of -2. So that's going to be 3 times -2 squared minus 5 times -2 plus 2. And that is going to give me 3 times -2 squared. -2 squared is still positive 4, so that's going to be 12 again. -5 times -2 will give me a positive 10 this time, plus 2. So that's going to equal 24. And when we plug it into our equation up here, we are going to end up with f of B was 2. So that's going to be 4 minus 24 over 2, that's B, minus a -2. 4 minus 24 would be -20. And then down here, remember, keep change opposite would give me a positive 4. And so that means that when I do -20 divided by 4, I end up with an average rate of change of -5. All right, so the next one that we are going to do is we are going to evaluate or find the average rate of change for this function at C and C plus H. And what this is doing is we are getting ready to look at the difference quotient. This is something that we will use quite frequently in calculus. Again, it's called our difference quotient. And once you perform the difference quotient computation, which is your C, C plus H, so what we have right here, once you perform that computation, then the average rate of change of a given function over any interval can be quickly found by identifying C and H and using your simplified equation that you get from this. So the difference quotient is used, like I said, a lot in calculus to determine the behavior of functions over intervals with smaller and smaller increments. So our difference quotient, it's something, again, you'll see if you move on to calculus, especially calc with applications or any calculus course. The first thing we're going to do, and this one's going to be quite long, is we are going to evaluate our functions at C and C of H, or C plus H. So f of C is pretty easy because all we have to do here is plug in our C. So we would end up with 3 times C squared minus 5C plus 2. Now we need to do f of C plus H. So that means we are going to have 3, and instead of x squared, we're going to have C plus H squared minus 5 times C plus H plus 2. So if I write that out, we're going to have 3 times C plus H times C plus H minus 5 times C plus H plus 2. And now we just have to multiply and simplify. So I'm going to distribute that 3 to this first term here. So I'm going to do 3C plus 3H And then I have to multiply that times c plus h minus, I'm going to go ahead and distribute the 5. 5c minus 5h plus 2. So now when I FOIL here, we are going to have 3c squared plus 3ch plus 3ch plus 3h squared minus 5c minus 5h plus 2. This is where it can get a little long, like I said. And then we're going to simplify it. So we are going to end up with 3c squared. I can combine these two terms, plus 6ch plus 3h squared minus 5c minus 5h plus 2. We can't do any more than that. So that is it. So now we're going to use what we have to do our difference quotient. All right, so what we need for our difference quotient is we need f of c plus h minus f of c all over, it should be b minus a, or in our case, it's going to be c plus h, which is our b, minus c. So that is going to give me, we are going to have 3c squared plus 6ch plus 3h squared minus 5c minus 5h plus 2 minus 3c squared minus 5c plus 2 all over c plus h minus c. So now we have to do a little simplifying. And the first thing I'm going to do is we have minus this second expression. So remember, it's like you have that negative 1 there. Let's distribute that negative 1. So that becomes a negative 3c. So we're going to do plus a negative 1 there. Positive 5c and a negative 2. So now what we need to do is simplify. If I look at that top expression, now I have positive 3c and negative 3c squared. So I can cross those two out. They cancel. I have a negative 5c and a positive 5c. And then I have a positive 2 and a negative 2. So that kind of helped me out a little bit, getting rid of some things. And then on the bottom, c plus h minus c, my c's would cancel. So on the bottom, I'm left with just h. On the top, I now have, what's left? We have 6ch plus 3h squared minus 5h. And everything else is gone. Now, I can do a little bit more simplifying. I can, on this top expression, if I notice, I can factor out an h from everything because it has a common factor of h. So I can make this h times 6c plus 3h minus 5 all over h. But then the nice thing is, because I factored out that h, my h's will cancel. So my final answer here is going to be 6c plus 3h minus 5. And it's a lot of work, but it really should in the end work out pretty nice and not be bad at all. So this would be our difference quotient for using the average rate of change for this equation. Right, so now we're just going to use our graph to look at determining when our average rate of change would be positive, negative, or 0. And here they have given us certain endpoints or intervals to look at, and they have labeled the first endpoint right here. This endpoint is A, this is B, and this one is C. So now we need to figure out between those points where our average rate of change would be positive. And again, this is important to remember. You read a graph from left to right. So between those 2 points, I want you to look at which one would be a positive rate of change. So like if I go from A to B, okay, it's going down, then it goes up a little, but A is higher than B. That's going to make that a negative rate of change. But if I go from B to C, we start down here at B and we go up to C. So that is going to mean we would have a positive rate of change from the interval of B to C. It would be a positive rate of change. Okay. Now, we already talked about this. From A to B, that is going to be our negative rate of change. So from A to B, that's our negative rate of change. And then, kind of wrote over it, if we go from A to C, they are on the same level there, the same y values. So that rate of change from A to C would be 0. And that is it for 5.2. I know it was a longer section, and that's why we'll look at just part of 5.3 this week as well.